Hi, and welcome to a little bit of a chat about what's going on with chemical formula. Some of you are well versed in this and will understand it totally without going too much further into it, but I'd still like you to go through the activity and reinforce in your own minds what you already know. There will be questions later on. By the time I put this through Edpuzzle, there'll be some questions there for you to just review and see how you're going with it. And hopefully you won't need too much more pushing along. If you are struggling though, it becomes a little bit easier if we go through this, and you can go through it as many times as you like. Right, so onward and upward. We've learnt so far, and most of us know the fact that when we start off with any chemical, we're going to have a basic difference between elements and compounds. Now notice I've left mixtures off this one. I didn't want to complicate too much. We're basically dealing with elements and compounds. As we know, an element is pure substance made of only one type of atom, and a compound are elements chemically bonded together. That's a nice, simple, workable definition for both of them. So if we follow the arrows down here and we go with the elements, we find that most elements are singles. In other words, we show them as occurring by themselves. And this is especially true for metals. Whenever we show, for example, sodium metal, we just show it simply as Na. We don't show it as Na2, Na3, Na5. We know though that in reality, sodium is really a whole group of sodium atoms together. But we do have other groups which do occur as single atoms, and we call those monatomic elements, and they're the members of our inert gases or noble gas group. So we have things like helium, neon, argon and krypton, and if you remember anything you've done before with the periodic table, we're in the right-hand column. Now if we go to other groups of elements, they tend to occur in groups. They do congregate in groups, and it's to do with electron configuration and a few other things. I'm not going to go into most of the reasons at the moment, but we have a lot of elements that exist in pairs. So we would call them diatomic elements, and actually they form molecules. And a molecule is a small group of atoms that combine and act like a single entity or a single unit. So for example, oxygen gas is actually O2 here. It doesn't exist as O. It does exist as O2. The same as hydrogen always exists as H2, nitrogen in the air is N2, fluorine F2, chlorine Cl2, bromine Br2, and of course their relative iodine as I2. Now of course we do have other forms of elements. There is another very, very common one which we have, and it's quite okay when it's up in the air, but when it's down at Earth's surface it's not real good, and that's this one. And it's a triatomic element, and it's a version of oxygen, and it's called ozone, and it occurs as O3, but it's still a molecule. Alright, so if molecules occur in elements, they are also going to occur in compounds. And we get molecules of two different sizes, and that's the only difference I'm going to concentrate on. Obviously there are things that I am not concentrating on at all that are included in here, but I'm trying to keep it a reasonably balanced and sensible length in this whole lesson. Right, we've got small molecules and then we've got large molecules. Macro means large, so macromolecules, and just normal sized molecules. We should know most of these normal sized molecules, like ammonia, NH3, carbon monoxide, CO, carbon dioxide, water and methane are some common molecules that we do find. Right, if we go to the larger ones, and these are probably easiest to remember, we have things like protein. that makes up most of our body. Our DNA is another macromolecule, and by macro we mean there's a whole heap of atoms joined together. Diamond is only made of carbon, but there are huge numbers of carbon atoms, so that's why it's included in this one. And we have diamond relatives, things called fullerenes, but that's another story, but they're also macromolecules. And most of the things which we call plastics, which are polymers, are also macromolecules. So hopefully that makes a little bit of sense so far. But when we show a macromolecule, or any molecule for that matter, or any chemical for that matter, we use a formula to represent the elements and their arrangements. Now it tells us the ratio of elements involved in the structure. It also tells us the total number in the whole formula part, and it also gives us which elements are actually present. So if we had to synthesize or make the compound, we possibly could. Now don't forget, when we are dealing with a compound, we call it a formula. When we are dealing with a single element, we call it a symbol. So things like H2 is a symbol, but CH4 is a compound, and so that's a formula. And if we look at it, we see we've got a capital C, capital H. So a simplistic way of thinking about it is if we have more than one elements, we'll have more than one capital letters present. So the number of capital letters effectively in your formula tells you how many of the different elements you have. Right, let's look at some examples. And I'll scribble all over this to help us try to remember. So I'm going to start off with looking at this one. So this tells us that we've got C, or carbon. We've got O, or oxygen. So it's a formula made of those two. We have 1 C to every 2 O, and we have 3 per formula unit. Alright, so we can break down what's in there, and we can do all these things just from our formulas. It doesn't matter how big or complex it is, it still works. So let's go to another one. NH3, or ammonia, we see that we've got N, which stands for nitrogen. Now it'd be really handy if you had a copy of the periodic table with you as you do this. H for hydrogen. I can see that I've got 1 N to 3 H's, and I've got 4 per formula unit. I think hopefully we're going okay with this. Alright, now this is a thing called sodium hydrogen carbonate, or more commonly called sodium bicarbonate. So let's look at capital letters. We got 1, 2, 3, 4 capital letters, so we're going to have 4 elements involved in it. We can have Na, which is sodium, H, which is hydrogen, C, which is carbon, and O, which is oxygen. Our ratios are 1 Na to 1 H to 1 C to 3 O's. And that means we've got 1, 2, 3, 6 per formula unit. Right, this one looks tricky, this one down here, but it's not. It's actually a form of clay, and actually we're looking at that. So let's go through it the same way. We've got capital A, capital S, capital O, another capital O, and H. Now O is going to be the same element, so we've actually got 4 elements only. Alright, so let's go through it. So we've got Al equals aluminium. Si is silicon. O is of course still oxygen. And H is hydrogen. So let's look at the numbers. This 2 here tells me about aluminium. So I've got 2Al, 2. This 2 is to Si, so 2Si. Then I've got something here that's a bit of a worry, because I've got 5 times O here, and then I've got another O inside a bracket which has got 4 outside the bracket. So like all math problems, the outside tells me how many of those I've got inside. Plus I've got another 4 times O, so I've got 9 O's. And then if I look at H's, I've got 4 H's. Alright, so that simply tells me I've got 2, 4 plus 9 is 13, plus 4 is 17, so I've got 17 per formula unit. I hope that has helped you a little bit, and I hope we have a bit better understanding of what's going on. There'll be others similar to what's going on here in our future messages. Alright.